Today, let's discuss about inner product spaces. Now we introduce the idea of distance or length into vector spaces via the structure called inner product spaces. Let us see the definition. Let V be a vector space over F. An inner product on V is a function that assigns to every ordered pair of vectors x and y in V a scalar in F denoted by this symbol which I have marked in red block, such that for all x, y and z in vector space V and all scalar C in field F, the following four properties hold. That inner product of x plus z y is inner product of x y plus inner product of z y. Second property, inner product of cx and y is c times inner product of x y. So these first two properties show that the inner product must be linear in the first component. Third property, conjugate of xy, conjugate of inner product of xy is inner product of yx, where this bar denotes the complex conjugation. And last property, that the inner product of x and x is positive whenever x is non-zero. Now in this chapter, we assume that the vector spaces are over the field F, where field is either real numbers or complex numbers. Now if suppose your field is real number, then the third property, xy bar is same as yx and this yx will be same as xy. Now we can extend this result for n vectors, that is inner product of summation I equal to 1 to n ai vi and y is equal to summation I equal to 1 to n ai into inner product of vi y. Let us see some examples. If you have vector space Fn, then x and y are two elements. Inner product of x and y is defined as summation I equal to 1 to n ai bi bar. Now we have to verify all four properties. The first property, x plus z comma y, that can be written as summation I equal to 1 to n ai plus ci into bi bar. We can rewrite this equation as summation I equal to 1 to n ai into bi bar plus summation I equal to 1 to n ci into bi bar, which is equal to inner product of xy plus inner product of zy. Now second part, inner product of cx comma y, you can see that can be written as summation I equal to 1 to n cai into bi bar. This c being independent of I can come outside of this summation, so we can write this as c into summation of ai bi bar, which is equal to c into inner product of xy. Third part, xy bar is equal to summation I equal to 1 to n ai bi bar bar. Now conjugate of bi is again bi, so we get that this is equal to summation I equal to 1 to n ai bar into bi, which is equal to ya, inner product of yx. Last, inner product of x comma x if x is non-zero is summation I equal to 1 to n mod of ai square, which is strictly greater than 0 if x is non-zero. So all these four properties are satisfied and this forms an inner product space. This inner product is called the standard inner product on Fn. For example, if suppose you have x is equal to 1 plus I comma 4 and y is equal to 2 minus 3i comma 4 plus 5i in vector space C2, then inner product of x comma y is first vector 1 plus I into conjugate of 2 minus 3i, which will be 2 plus 3i, plus 4 into conjugate of 4 plus 5i, which will be 4 minus 5i. So this is equal to 15 minus 5 iota. Whenever your field is real numbers, the conjugations are not needed. Second example, if x, y are any two vectors on a vector space V, the inner product can be defined as inner product of x comma y. And if you have any positive number r, then we may define another inner product using the previous inner product as r times the inner product of xy. All four properties of inner product will be satisfied by this new inner product. But if R is less than equal to 0, the fourth property won't be satisfied. So R must be greater than 0. Third example, let us consider the vector space of real valued continuous functions on 0, 1. For any two functions f and g, inner product of f and g, we define that by integral from 0 to 1 ft gt into dt. Now clearly integral is a linear function in f, so we get first two properties are satisfied. Third property is also satisfied because it is a real valued function. So integral of fg bar will be same as fg. Now for fourth property, if f is not equal to 0, then for some point x naught there is an interval which is non-zero. Then inner product of f comma f is equal to integral of 0 to 1 ft square dt, which is positive. Next we define conjugate transpose. Let A belong to vector space of matrices of order m cross n over f. The conjugate transpose or adjoint of A is the n cross m matrix A star such that A star ij is equal to AJI bar. So we are taking the conjugate and transpose of a matrix. For example, if you have this matrix A, I 1 plus 2i 2 3 plus 4i, we take the conjugate and transpose. So A star will be minus I. Now 1 plus 2i will come at the second row, second column position. So 1 minus 2i. Conjugate of 2 is 2. It will be 2. And the last one, A2, the position A22 will be 3 plus conjugate of 3 plus 4i. That will be 3 minus 4i. Next example, if you have a vector space of order all matrices of order n cross n, we define the inner product of AB as trace of B star A. Trace is sum of all diagonal entries. So let us start with the first property. Inner product of A plus B comma C is trace of C star into A plus B. This is equal to trace of C star A plus C star B, which is equal to trace of C star A plus trace of C star B, which is equal to inner product of BC. Second property, inner product of scale, let us take scalar k. So inner product of ka comma b is trace of b star into ka. Now k being a constant number can come outside. This will be equal to k into inner product of ab. Third, inner product of ab bar is equal to trace of b star a bar. Now trace of b star A is sum of all diagonal entries, so we are writing that as summation I equal to 1 to n pii bar. Now using property of complex numbers, this is same as summation I equal to 1 to n pii bar. Now pii is what? Bij star into AJI bar. Now we are separating the bar, we have Bij star bar and AJI bar. Now see, Bij star is conjugate transpose and we have one more bar. So 2 conjugate is cancelling, so we are getting BJI, only one transpose is left, and AJI bar is AIJ star. So this is equal to summation I equal to 1 to n, j equal to 1 to n, AIJ star into BJI, which is equal to summation I equal to 1 to n QII, where this Q is A star B, which is equal to trace of A star B. So this is equal to inner product of BA. Now fourth property, inner product of AA is trace of A star A, which is equal to sum of all diagonal entries. So A star A II denotes the all diagonal entries. Now we are writing this as A star IK into AKI. Now in the next line we are writing this star A star IK as A bar KI into AKI, which is equal to summation I equal to 1 to n, summation k equal to 1 to n, mod of AKI whole square. Now since if A is not equal to 0, this AKI is not equal to 0 for some k, so this inner product A comma A is greater than 0. Now this inner product is called the Frobenius inner product. Now if a vector space V over field F with a specific inner product is called the inner product space. If that field is C, we call V a complex inner product space, and if field is R, real numbers, then we call that V as a real inner product space. Also, if V has an inner product space x comma y and W is a subspace of V, then W is also an inner product space when the same function x comma y is restricted to the vectors x, y from W. Now let us see this theorem. Let V be an inner product space, then for x, y, z in V and C belonging to F, the following statements are true. First part, inner product of x comma y plus z is equal to inner product of x comma y plus inner product of x comma z. Then let us see the proof. Inner product of x comma y plus z is equal to inner product of y plus z comma x bar, which is equal to inner product of yx bar plus inner product of zx bar, which is equal to xy plus xz. Second property, inner product of x comma cy. Now the c is in the second position, so inner product of x comma cy is equal to c bar x comma y. So inner product of x comma cy is cy comma x bar, which is equal to c bar into inner product of yx bar, which is equal to c bar into xy. Inner product of yx bar is equal to xy. Third point, inner product of x comma 0 is equal to inner product of 0 comma x is equal to 0. So inner product of x comma 0 is 0 bar into x comma 0, which is equal to 0. And similarly, inner product of 0 comma x is equal to x comma 0 bar, which is equal to 0. Now the inner product of x comma x is 0 if and only if x is equal to 0. So if x is equal to 0, then inner product of 0 comma 0 is 0, and if x is not equal to 0, we know that inner product of x comma x is greater than 0. Last, if x inner product of x comma y is equal to inner product of x comma z, then for every x in y, then y is equal to z. So if inner product of x comma y is equal to inner product of x comma z, then we have inner product of x comma y minus z is equal to 0 for every x in V. This implies, in particular, we take x equal to y minus z, so we have inner product of y minus z. Y minus z is equal to 0. This implies y minus z is equal to 0, that is y is equal to z. Please observe that the first two properties show that the inner product is conjugate linear in the second component. Now let us define norm. So if V is an inner product space, then for any x in V, we can define the norm or length of x by norm x equal to under root of inner product of x comma x. Let us see this example. If V is equal to Fn and x is equal to an n tuple a1 a2 an, then norm of x is square root of summation I equal to 1 to n mod of ai square. This is the Euclidean definition of length. If n is equal to 1, then norm of a is equal to mod a, which is the normal definition of length in real numbers R. Next theorem, let V be an inner product space over F. Then for all x, y in V and C in F, the following statements are true. Norm of Cx is equal to mod C into norm x. Second, norm x is equal to 0 if and only if x is equal to 0. So this norm x must be greater than equal to 0. Third is the Cauchy Schwarz inequality, that is mod of inner product of xy is less than equal to norm x into norm y. And fourth is the triangle inequality, that norm of x plus y is less than equal to norm x plus norm y. So let us see the proof. First part, norm of Cx is equal to square root of inner product of Cx into Cx. Now we take C common from the first and second component. The second component will give you C bar. So we have C into C bar into inner product of x, all this raised to power half. This is equal to mod C into norm of x. Now second point, norm x is equal to under root of inner product of x comma x. We have already seen in previous theorem that inner product of x comma x is 0 if and only if x is equal to 0. Let us see the Cauchy Schwarz inequality. Now if y is equal to 0, we get the result immediately. So we assume that y is non-zero. Now for any scalar c in F, we have norm of Cx minus Cy whole square is greater than equal to 0. So we say 0 is less than equal to norm of x minus Cy whole square, which is equal to inner product of x minus Cy comma x minus Cy. This we can write as inner product of x comma x minus Cy minus C into inner product of y comma x minus Cy. Now again simplify this, you will get this equal to inner product of x comma x minus, now C is in the second component, so we have C bar minus C bar x comma y minus C inner product of y comma x minus minus plus, and C from the second component will give you C bar, so we have plus C bar inner product of y comma y. Now if we put this C as inner product of xy upon inner product of yy, we get the inequality 0 is less than equal to inner product of x comma x minus mod xy square upon inner product of yy. Just put C is equal to this inner product of xy upon inner product of yy. So this is equal to norm x square minus mod inner product of xy square upon norm of y square. Now put this greater than equal to 0, you will get the Cauchy Schwarz inequality. Next, for the triangular inequality, consider norm of x plus y whole square. This is equal to inner product of x plus y comma x plus y. Open this inner product, you will get inner product of x plus inner product of yx plus inner product of xy plus inner product of yy. So this is equal to norm of x square plus twice of real part of inner product of xy plus norm of y square. Now this real part is less than equal to mod of inner product of xy, and mod of inner product of xy is less than equal to norm x into norm y by Cauchy Schwarz inequality. So we get this norm x square plus 2 times norm x norm y plus norm of y square, which is equal to norm x plus norm y whole square. Now let us see the next definition. Let V be an inner product space. Vectors x and y in V are orthogonal or perpendicular if this inner product xy is equal to 0. A subset S of V is orthogonal if any two distinct vectors in S are orthogonal. A vector x in V is a unit vector if norm x is equal to 1. Finally, a subset S of V is orthonormal if S is orthogonal and consists entirely of unit vectors. Now, if suppose you have a set S equal to V1, V2 of vectors, then S is orthonormal if and only if the inner product of Vi, Vj is delta Ij, the Kronecker delta, that is, it is equal to 1 whenever I is equal to j, otherwise it is 0. Also, if we divide each vector by its norm, V1 by norm V1, V2 by norm V2, then this will be each vector will be a unit vector. This process of multiplying a non-zero vector by reciprocal of its length is called normalizing a vector. Now let us see this example. In F3, if you have these three vectors, vector V1 equal to 1, 1, 0, V2 equal to 1, minus 1, 1, V3 equal to minus 1, 1, 2. Now we have to see that this is a orthogonal set. So consider inner product of V1, V2, V1, V3, V2, V3, all will come out to be 0. It is not orthonormal. Calculate its norm. It will not be equal to 1. Now if we normalize the vectors in this set, that is divide every vector by its norm, then this will come out to be orthonormal set. Now let us see the last example. Inner product space of continuous complex valued functions on the interval 0 to pi, where we define the inner product as inner product of fg is equal to 1 by 2 pi integral 0 to 2 pi ft gt bar dt. Now we introduce an orthonormal subset S of h. I is the imaginary number such that iota square is equal to minus 1. Now for any integer n, f and t is defined as e to the power iota n t, t lying between 0 and 2 pi. Also recall that e raised to power iota n t is cos n t plus iota sin n t. Define S as fn, where n is an integer. Clearly S is a subset of h. Using the property that E iota t bar is equal to e to the power minus iota t, because e to the power iota t is equal to cos t plus iota sin t. E iota t bar means conjugate of that, that will be cos iota t minus iota sin t. Now inner product, whenever m is not equal to n, inner product of fm fn is equal to 1 upon 2 pi integral 0 to 2 pi e to the power iota mt into iota n e to the power iota nt bar dt. So this is equal to 1 by 2 pi integral 0 to 2 pi e to the power iota m minus nt dt. This is equal to integral value is equal to 0. Also inner product of fn is equal to 1. We can see that. So basically inner product of fm fn is equal to Kronecker delta mn, that is it will be equal to 1. That is inner product of fm fn is equal to Kronecker delta, that is it will be 1 whenever m is equal to n, otherwise it will be 0. This defines inner product spaces and norms. Thank you for watching this video.